you should have the understanding, the idea about the memory organization, cache organization, and also about the pipelining hazards, all these topics. So I think this part was done some of your architecture courses. So what I want to know for all of you, should I recap again some parts of those parts, or should I skip that and directly go, assuming that you know about the cache organization, assuming you know you have that ISA concept, you have that pipelining hazard concept, and I will go directly to the design. So can you tell me that is it okay if I skip that, or should I brush up the previous part a bit, maybe in 1 or 2 hours, and then I will go to the actual implementation part? So what is okay for you?
Brush up, ma'am.
Brush up. Okay. Then Monday I will do that. Then I will start that implementation part. Okay. Okay. So let's start today. Maybe it's fine. Okay. Sorry. Okay. So let's start today. Today, so far we have talked about hierarchy, concurrency, how to handle those things. I think those are a bit clear. If you have any questions, let me know. I will again go back to that part or those slides. So today one part was mainly about FSM, that how we are going to handle feedback in our feedback modeling when we are considering our FSM. So that small part we will discuss today. Then we will move to other types of models. Other models means we have seen that FSM is a very strong, FSM or in state chart, if we think about state chart where we are supporting hierarchy, concurrency, all these things, is a very strong modeling strategy we can actually follow. But still, FSM is also having some types of limitations. So that is mainly in terms of when we are talking about distributed scenario. So for that, what will be our suitable modeling strategy? Or when we are talking about FSM, we know we are considering about some event-driven situations. When there is some event, then we are considering the state changes, and based on our modeling is mostly focused on that. But is it if FSM really required, or what is the solution when we are considering data-oriented model for, let's say, signal processing? When we have to consider just some amount stream of data that we will do some and we will want to do some operation on it, let's say filtering on it, and then that will give my output stream of data. So for that processing, what is the what may be some simpler modeling solution? So all these aspects, maybe other than FSM, all a few different modeling aspects, modeling strategies we will discuss. Okay, so just complete this feedback related FSM part. Here you can see these situations can occur in your, sorry. These type of feedbacks can be very common in your design. If there was no feedback, then these type of designs you could have modeled easily by the knowledge of your hierarchy, by the knowledge of your concurrence. But when there is some amount of feedback, how you can think and consider that feedback in your modeling? Now we mainly do that in special type of model of computation that is called synchronous reactive model of computation. This is synchronous reactive. What does it mean? In synchronous reactive model, we consider everything is a discrete system. This is a discrete system where signals are absent all the times except at ticks of some global clock. That means there is some tick generated from a global clock, maybe some global timer. At that time, we will consider the presence of the signals. Okay. So what does it mean to understand feedback means? At particular tick, whenever is it what is it?
Are you presenting, ma'am?
Yes, I presented.
We can.
You can't see? Okay, I will. You can't see my slides, right? Okay, I will.
Yes, ma'am, your screen is not visible.
Okay, wait. I will again do it. Okay. Sorry. Now, can you see the slides?
Yes, ma'am.
Okay. So, what we are discussing today, we are trying to handle feedback. These can be different feedback scenarios that can be very common in your design, and if your requirement maybe, and you have to model that. Now, if this, you can understand this type of feedback, if that, sorry. Wait 1 second. If there was no feedback, you could have designed this part, maybe this part and this part, with the knowledge of your concurrency and hierarchy. But some added information or knowledge should be considered when we are considering these part. Okay. So to do that, we basically consider a special type of model of computation that we consider synchronous reactive model of computation. That is not much different what we have discussed. Just you have to consider your modeling, or you have to keep in mind that at that time we are just considering some discrete systems where signals are only present with some ticks of global clock. That means you are just considering the change of signals or the effect of signals when there is some tick of global clock. What does it mean? At some nth clock, maybe you have to this system, you have given some input and you have got some channel. So at that nth, tick of clock, whatever output you are generating, that should be a valid input as well as a valid input, right? So this is a valid input. You can think in this way. Otherwise, concept is very similar. That at a particular tick, whenever you are getting a tick, at a particular tick, whenever you are getting a particular output, that output should be a valid input in the next tick. So that way you have to model a thing your FSM design. Feedback related FSMs. So this is a simple feedback where you can see you are having one output S, and that again is going as an input to the system. So to model that, what is the simplest strategy? That we will think about two states. Maybe they're according to the working policy of your this block F. There may be some intermediate one or many states in between this S1 and S2. But we are just considering these two states where in one state we will consider effect of input, and this state we will consider when there is no input. What does it mean? That means whenever you are in this state 1, okay, and you have this input X, then this state will remain in this input handling state. After that, maybe there will be different intermediate processes. Here we have not shown, here we have ignored those states. And finally, it is going to some state when it is either there is no input or there may be some input. If there is an input, it is making a transition. Input, see, this input is X, it is making a transition to the state S1 again. But if there is no input at a certain state, it is generating some output. Basically, a normal FSM, you can think. At some state 1, you have actually accepted your input, that is your X. You have, according to your logic, according to your specification, whatever it may be, you have done some computation and you have reached up to state 2. At that state 2, there is no state, no input. If there is no input, then your FSM, your system, will remain in that state 2. If there is, according to your logic, if there is some input X, then it will make a transition X. A transition from S2 to S1 based on this X. Now, this is pretty simple. What important part is notice is that at this state S, you are generating Y, output at a particular maybe energy. And this output, you have to, that's why we are considering the notion of synchronous reactive. That means your system, your model is reactive according to the text. And in the next state, or we can say in the next state, that output is basically acting as an input to your state S1. So that way, it is quite similar, whatever we have discussed, just a bit addition about that concept of reactiveness with respect to your global tick or global clocks. So that way, feedback can be modeled easily or simply. So this is the this is the description that is written, that at nth tick, whatever you are considering as output, in the next you are considering the same as your input to your feedback model. This is a simple thing I think we have not discussed before. Okay. Next, we will move to other data models. So first, we will start with that we have already talked about, that we will start with data flow model. So for whatever we have discussed about some event is taking place, and based on that, we are doing some state transitions. And that was the main notion of FSM. In data flow model, see what we are considering. Here you can see. We describe system behavior as a set of nodes. Representing transformations. Okay, here my node, you can check this example actually. Then you can understand. These are the transformations. We are considering some set of nodes and set of arcs maybe. So these are considering your data inputs. This way, data model is based in this nodes are giving you the idea on this data what operation or what transformation you are applying so that you can go to the next state. In the next state, again there is, in the next study, you can go to you can send that data as the input of the next node. So you are applying this transformation on this E and B, and that the output of this node you are sending as an input, maybe as a final result or input to some next node. That way you are just see here is no concept of event driven or incorporating some events, nothing. It is purely data related, where you are applying some operations on your data and you are processing that you are passing to your next node. Similarly, this you can think this is more specific because these type of data models are suitable in DSP or signal processing related things. So these are few operations or we can say few transformations related to that domain. You can modulate, you can convolve, you can transform, and apply any other transform. And important part is that this data model is maybe synchronous. Okay, and maybe you can apply parallel processing in different operational nodes. So this is the basic idea of data model, that for FSM is not always needed, or there are some other kinds of models, because so far whenever we have started discussing about modeling, we are just discussing about FSM. So it is not only that we are only having FSM in modeling scenario, we can have these different modeling techniques. Now we will discuss some concrete limitations of FSM itself, and for that we are thinking about some other description languages. So one main thing is that use of shared memory. If you are thinking, sorry, there will be no this is a continuation. When you consider this state chart related hierarchy and concurrency, and whenever you are thinking about some modeling, shared variable related applications, we have seen in different types of scenarios, different types of examples here. Just a second, excuse me, 1 minute. One minute, okay. Just. Okay. Okay. Can you see the slide? Hello? Hello?
Yes, ma'am.
Okay.
Yes.
So what we are talking about, that so it can it can allow synchronous data flow also between different nodes. So this is all about data flow with OPR here. Sorry, we were talking about this specification and description language. In this case, what we mentioned, that when we talked about state charts, where we have considered hierarchy and concurrency along with our general FSM, there one limitation is that the concept totally developed based on shared memory. Now this shared memory concept is okay when actually your processing units, they can share the memory location where you are actually storing your shared variable. But for distributed applications, that is not proper. So to handle that, we will see what is the concept developed in HDL. I mean, what is the different notion developed in HDL? That is the specification and description language. It is again based on some typical signs. You can see here, you will see the state will be represented by this symbol. This is the initial state, this is the input state, and this is the output state. Okay. So now we will see first how FSM, now we understand whenever we are having some FSM, specification, how we can translate that to some FSM. Now we will see how this FSM can be mapped to some HDL with language. So here, this is this initial state. This is the initial state. See, this is the initial state. That is not defined, so we have kept it blank. After that, these are the states. A, B, C, D. These are the states. Okay. And this is the GURD and the output action. So GURD is basically considered as the input and output is considered as this with this symbol. So whenever based on each transition, we are having this GURD and actions, we are mentioning those in this way. B, B to C, C to D, and so on. Now you can think, if we think about these other related to a particular process, like a particular process is just handling these A to B transition. B to C, another one process, and we are mapping them to different processes. Okay, so that you can think that may be your distributed application. Now the next question arises. Okay, so you can check the next levels also. I'm not going into this. From E to A, again there are two parts. That's why it is given this way. So E to if there's this condition F is given, input F is given, output V will be generated, and that will finally move to this state A. And from E to K, if this K input is given, then there is no action. That's why this output is empty, and this E to K, E to A state transition is taking place. So rest of everything is same. You can consider. So this is for one process when we have considered the FSM. Now, if we develop multiple such processes and we distribute them in different.
Ma'am.
Yes.
Ma'am, in the last slide.
Yeah.
The initial state, like ma'am,
yes.
How are we finding that? Like it is.
The initial state is not. Here it is not specified. It is not given. See, this is okay. Before A, nothing is given. So we are thinking about if there is some initial state or initial condition, we will put here. Okay, since here nothing is given in this example, we have just kept it blank. Okay, if there is something, we can put it here. Fine. Next, this way we may design one single process, or maybe you can think that whatever your specification is, whatever different transitions are, you can divide in these type of subblocks. And in your distributed scenario, if for your state specific computations is too heavy, you can, distribute them in different processes. And you can send them to different processes. Now, sometimes in distributed scenario, these different processes may not have access to your shared variables. That's why these variables are declared locally, and you need some inter-process communication technique in HDL, and that is done based on these type of message queues. Okay. So that is the queue means what? This is first in, first out. That means your process is generating some output that they want to send as an input to the another process. Maybe here we can consider this example of process 1 and process 3. So process 1 is generating some output. It is putting in the some queue that is maintained by this, and maybe that is read and maintained by this process 3. You can see this one. So this, and not only the process 1, process 2, process 3, process 1, process 2, and maybe if there are n processes, everybody as and when required, as and when they want to interact or share some values, exchange some values with process 3, send some value to some process 3, it will make use of this FIFO queue. FIFO means first in, first out. When whatever signal will go in first in this queue, process 3 will extract that, and it will take, it will use that in its next level processing, maybe processing input. Like these type of inputs may now come from local variables, or this type of inputs may now come from this type of, from the inputs of this FIFO-Q. So both are possible. So this is some one example of asynchronous message passing, where everything is going on in an asynchronous basis. Whenever, as and when required, these processes are making use of this queue. So for this, now you think to implement this, what you need? You need one process interaction diagram, because this interaction diagram will give you the idea which process will be communicating to whom, and based on that, and what will be the intensity, or what will be the, maybe you can tell the count of these interactions. Because whenever, that is the main limitation, will come into this, whenever you are considering this type of Q FIFO related feature, FIFO-Q related feature, what may happen? There are n processes and they are continuously sending some input to this FIFO-Q. Okay. But process phi is not extracting in the same way, so that the number of inputs in the FIFO-Q may be increasing beyond the limit of the, beyond the length of the queue you have actually set. So how will you actually predetermine or pre-calculate? It is important to pre-estimate that what will be the length of this FIFO-Q. Okay. So for this is the process interaction diagram that is prepared. So what does it mean? This interaction diagram can be used to visualize which of the processes are communicating with each other. In the case of SDL, the term, that is one important thing, signal denotes inputs and outputs of the model automator. So now come to this diagram. How this process is interacting, you can see this is process 1 and this is process 2. Maybe these two communication of them you are considering inside a block, and they are passing, they are exchanging, maybe see process B1 is sending this signal to process B2. So this is the signal. Now, how they can communicate? In direct way, maybe there is one mother process and it is sending same information to its one or more offsprings. So in that way, that signal can be sent to this way to the offsprings. Otherwise, it can send the communication to via some particular channel with some particular IP. Okay. So based on that, not only this process interaction diagram, you have to also consider some hierarchy. That means, because see, here you have inside one block, you have considered these two processes and you have combined their communication and you have considered a block. Now this block is basically a small part of your whole system. So you have to consider these components or subcomponents inside your system, and that way your system maybe look like this. So your system may be whole system that is composed of these blocks. Again, this one B block, it is composed of this type of subcomponents and their interactions. So whatever output you are sending from this block B, see these C4, C3, those are basically these two output. It is going to some other main blocks where there are different types of subcomponents are present. Okay, so there is a sort of hierarchy again. Of course, you remember in FSM also we considered hierarchy, and here also, because when you have you are having complex embedded systems, embedded designs, you should know your modeling strategy also should support how you are going to handle this hierarchy. So this is your SDL hierarchy, where you have a main system, your main system, main block. You can consider that as your root. Then you can consider back into the main components, then the subcomponents, and so on. The important part is that at the base level, these components will actually define the processes and their intermediate communications. That means at the lower level, they are defining how you are actually interacting between the processes inside those components. That's why it is written blocks at the highest level are called systems. That I think you can understand. This is the highest level. And at the block at the lowest level, you are considering the process interaction diagram. Blocks to sub-blocks, then sub-blocks to subcomponents, then to processes, and at the root level, that is the process interaction diagrams, whatever processes you have and how you are interacting with them. So these are the two features. One is the FIFO queue and another is this FIF HDL hierarchy. These are the two main features that help HDL to be used in distributed scenario. And that is the main advantage we can think of HDL over FSM. So this is some added features, of course, that should be there. Handling of timers. It is shown how you can handle timers. So timers basically incorporated here based on some set and reset function. You can see this is a timer and there is set and reset functionalities. So set, what is written, I think you can see set now plus P. That means from now you are setting some P seconds or P time units. So this is how you are actually setting up the time units. You are acting up, and then reset means that is straightforward. There is no concept of adding some time units and all. So you can see in this example what happens. In this case, if there are two things. When you are incorporating some timer related transition conditions, this is something like that. That from this E to A transition, you remember there are two conditions here that we have defined in a different way. You can think here either it may happen E to A transition. There is some input F that will set some action V, action output V. Then it will reset some clock and then it will set to A. Other than that, if there is some input T, then it will immediately reset that timer T, and once that timer is in the reset condition, it will make a transition from E to E. Okay, so this is a direct reset. It is not caring whether you have actually got this input F or not. Okay, so this is how, of course, that these features should be there when we are talking about embedded system design or this complex system design. This is how HDL is actually handling the timer or incorporating timer in the modeling features. So this is, now you can understand this as an example how you can understand this HDL in computer networks. That means this is your whole system where you are having multiple processors, processor A, processor B, router, whatever it may be. They are connected based on some queues, message queues, and this block, inside each block processor A, there are different layers. Basically, what we can think, whatever we have discussed, remember, in this block processor A, maybe there is a single process going on, or some multiple processes you have added and cascaded together. But each layer can be typically realized by a single FSM. Now you know how to translate a single FSM to the language of HDL that we have discussed already here in the first slide. This is, you have one FSM and you are translating them to some language, to some representing them on the basis of the symbols related to your related to your HDL symbols. So this is the first step. This is how you're realizing these layers. Next, these layers inside one processor, maybe they are having shared variables and they can communicate. But again, what is the limit? So this is the basic idea of HDL and why we are thinking of HDL over FSM. But what is the limitation of HDL? The main limitation is the use of this FIFO-Q that we have already mentioned. Remember that FIFO-Q, whenever you are actually going for practical implementation, you are actually implementing, you are assigning some particular length for that Q. But there is a chance that when your maybe end processors are communicating together and there are different exchange of signals, it may happen that size of that FIFO-Q may be increasing in such a way that there is a chance of overflow. For this reason, when we are moving to HDL, we have to get a pre-estimate of these different interactions. Okay, so that is not a very easy job, because when we are actually modeling a dynamic scenario, dynamic situation, it is not always possible. I mean, it is very not actually, we can take some higher estimate and all, but it is a tough job to actually limit or actually give the finite length of this FIFO-Qs in advance. So this is a limitation of HDL. So is there any question till now?
Ma'am.
Yeah.
In the slide before that, your voice got stuck for some time.
Okay, cool. Which part? I will repeat that part.
This part, yeah. This slide.
This part, right? Okay.
Yeah.
Okay. See, this is the practical example, which this is a computer network scenario that I can model with this my HDL. Okay, so wait, just a second. Okay. So wait. Okay. Now, in these computer networks, what are there? There are different processes. You can see processor. You are considering the overall system. Your system now includes these different subcomponents: processor A, processor B, processor C, router. And you understand, when there are these type of multiple processes, they all are trying to communicate. Now, when you are modeling using HDL, you have to know how we will start with. Okay, so we are starting with different processors. These are the different processor blocks, and we are defining the processes we are considering in these processor blocks in different layers. Maybe there in that single processor scenario, there is one single processor, and if it is a multi-processor scenario, there are multiple processors, and we are considering multiple processes. We are considering maybe and they are interacting. If there is the possibility that they can access those some shared variables, then they are doing that. But inside one processor, each of these layers, you can consider those one single FSM. Okay. For each layer, you can think and model them as a single FSM. How will you do that? You can go back to our first slide. You can think, we have started discussing when we know our specification of that particular process or that particular layer. You can think now. You can actually from that layer specification, you can come up with the FSM description FSM description of that specification. And from that FSM, you can actually move to this HDL language representation. There you can actually represent those steps in this way, inputs this way, output this way, and whatever we have discussed. So now you understand how to, in this block processor, how to model these type of layers, FSM to HDL. This way you are actually modeling each of the block processes. Then you have to communicate them. You have to make some strategies that they can communicate. For these communication, remember we already discussed about designing that FIFO queue. So those FIFO queues will be used here for the inter-process communication. Okay, so this is a practical example where your HDL modeling can be actually effective. But what is the limitation in this scenario? When you are actually modeling this using this HDL, now is it fine? Hello?
Yes, ma'am.
Yeah. So when you are actually designing this scenario with your HDL strategy, the main limitation is whatever we have discussed about that FIFO queue length. It is difficult when you are actually modeling a dynamic system. It is difficult to anticipate how much signals, because if you go back what we have discussed, these signal interactions are taking place and any process is storing to this particular FIFO queue whatever signals that are coming directly to this FIFO queue, and process 3 is fetching from this queue. So for that, you have to, when you are actually practically designing this model, realizing this model in this way, you have to understand in detail what can be the maximum size of this FIFO queue. What can be the maximum signals coming from different other processes to this queue. And that is a difficult task. That's why this is one main challenge main bottleneck when we are trying to adopt this HDL, that FIFO queues must be of finite length, and to make a practical input, to do your practical implementation, you have to make a prior estimate of this queue length, and that is that is a typical challenging task. So this is the thing about HDL. We will come back again, not exactly an HDL, but a tool related to HDL, that is UML and the extension of it. So there we will see how the different layers can be developed, can be modeled, and what are the different features of UML. So if we will, maybe in the next class, we will discuss that in detail. But here we come next, we'll start discussing about another typical modeling strategy, that is called Petri-net. Petri-net is very useful in this type of causal dependencies. So first let's take an example, so how the Petri-net looks like. Then we will come back formally how we will define different parts of it. Okay, so Petri-net basically consists of these type of places. We will see transitions. This is transitions and some events. What does it mean? You can think about a place handling one token. That token, this place, you can consider as a state. So these token there is different transitions this token is receiving based on some event. Okay, so this is a state where train wanting to go to right. Okay. Then this event is occurring. This box, rectangular box, I mean mark that, we use that for realizing events, for understanding events. So this is one event occurring, train entering track from the left. So this is one state, this is one event. And based on this event, this token is moving here or here. So this is maybe the next, you may come to this example. I mean, this is the same example, different states are given. It's shown actually. It will be easier for you to understand. So you can see this token is here. This event is occurring and the token is moving to this point. Okay. So basically that state is changing based on some event. So the same thing you can check here also. There are some more events going on, and based on that the token is coming here. And here Petfinit is also useful. We will come back next again with some detailed example. That if some situation happens, then that this token is moving here to here and then here, and in some cases it may happen that this place, maybe there is a possibility occurring that these tokens may in the next transition may be coming to this place, and this token is also coming to this place. Not exactly in this direction, some other directions are there. We will come up with that again to this example. So Petfinit is also very useful for collision detection. But the main idea is Petfinit is all about some state transitions and related to events. We will see how the formal definitions, and then with some examples we'll see how that works. So when we are talking about Petri net, what does it mean, this net? Net can be defined in this way. Okay. So N is equal to CEF is called a net if and only if the following holds. What are the conditions? C and E are disjoint sets. Basically C, we will term it as letter. This will be our conditions and E are the events. Okay. And this is the flow reaction. Flow relation. Okay. Here if you think this is my condition, or this you can see when this token is inside a place, that is basically defining one condition. And next, this is the event. So this is C, this is E, and this is if. Okay. So flow relation is basically a binary relation. This relation considering your conditions and events. So what is a pure net? Pure net, in case of, to understand the pure net, we have to understand what we mean by loop. Okay. Loop means, you can see this formal definition. Let for the net n be a net. Now you know what we mean by net. What are the conditions to be satisfied to n to be a net? Here we have x, one element of C union E. And this is the precondition of x. So we are defining precondition in this way. You can see a dot prior. Okay. And here you can see a dot after x. So these are defining the preconditions and post conditions. That is, you can see here. This is dot x, you can say. This is called the state of preconditions. How you can define? Where to satisfy this x and maintaining this flow condition, you need to have this preconditions. And this is the, similarly you are defining the post conditions. So that is this is the set, is called the set of post conditions y given xfy. Okay. So y, you know, that is a particular post conditions, and x is your condition, and even this unit you are taking the this is the element from C union E. That is a condition union event set. And F is coming from the flow relation. That is, you are satisfying some flow relation based on some given conditions and events. Where for that you have to do that, you are specifying some set of preconditions and some set of post conditions. So that way, if you have some set of preconditions and post conditions, then you can define a loop in this way, where see CFE, that means some condition, some flow and some event, and event, flow, and if this relation holds. Okay, so and where is N? N is pure if F does not contain any loop. Now, what does it mean? Just take this one example. This is very simple, and you will understand that. In this case, if this is the scenario, and it is called simple if no two transitions have same set of preconditions and post conditions. Maybe you can consider this is one transition. Okay. For this transition to happen, if the preconditions and post conditions are same, maybe there are two conditions T1 and T2. There are two transitions. For them, if the same set of preconditions and post conditions, then we cannot tell them some simple names. Okay. Okay. For the loop, I think it is clear that you're having some condition, then that condition is leading to some flow relation, and that is leading to some event. And similarly, the same event is leading to some flow conditions, flow relation, and that flow relation again satisfying some post conditions. If both holds true, that means for same condition, you can see in your modeling, some event is going to there will be some event E will happen for some precondition C, and when this E occurs, even E occurs, according to your flow relation, some post condition, the same whatever that precondition was there for your even E, that is the same post condition when your even E occurs. In both cases, this is C. In this case, you can consider that is a loop. And when we can design a net when there is no loop, that means the loop is pure, and the simple means no two transitions in a particular net will not have same set of preconditions and post conditions. Okay. So based on these assumptions, there are different types of nets. The different definitions of nets are given. If there is at most one token per condition, okay, then that is called the transition net. But that is the limitation of transition net. There is one token per condition. That what does it mean? Here, if you go back to this part, let's say for this condition occurring, okay, you can see this. Maybe we can focus on this part. Based on this event, some transition will happen. For this, what may be the possible conditions? These possible conditions may come from these tokens, and these possible conditions may come from also these tokens. But in case of your general net, place of transition nets, at most one token per condition is possible. So that is the limitation of your place and or transition nets. So how will you define that? I think we can take one example, then we can come back to this formal design definition. That will be easier. Or we can see this. Okay, let's see this definition once first. Then we will go to the one detailed example that will help, I think. So how will you formally define this place or transition nets? See, this is called a place or transition net. Well, these are the different. I mean, this is a tuple, you can think. So this is a net where we are having places. Now you know places, transitions, and flow relations that we have already talked about. Other than that, we are adding another extra feature that is called the capacity. Okay. Also, we are adding width of the graph edges. And also, we are having some initial marking of places. Okay. So this is the improvement of conditional conditional or event-based transition that we have seen in the first one in case of simple type of event-based transition. There we have not considered these type of mapping weights or mapping capacities. What does it mean? See this example. Maybe this is a transition Tj. Okay. For this, you are having this input edges and these are the output edges. That means when you are actually considering some event, this transition and that will by that this transition will occur. For that, you are expecting some inputs, some tokens from these input edges. Now you see here some previously whatever examples we have seen, see here in this case, we have only considered one single token at each place. Here in this place or transition nets, we are considering some capacity associated with each place. That means now this place, it is not necessary that each place will hold only one token. Only one token means it is not necessary. It will at each place or each state will only hold one single transition condition. So there are multiple tokens possible in each place. And that is the maximum number of tokens possible in each place defines the capacity of this place. Okay. So based on this capacity, that maximum capacity we're defining, and these are the edges, each weights. Each weights means you see 1, 3, 2, etc. That means it is not necessary for these transitions, the edge associated with it will always use all the tokens. That means here see you have 3 tokens. That is the capacity of these places. But for this particular transition, the edge associated with it is having only single weight. That means only single token from this place is necessary for this transition to make possible. Similarly, here this is 3. That means all these tokens, all these conditions will be used. From here, the total capacity is 3, but here only 2 can be used to make this transition possible. Okay. These are the preconditions of these transitions. Now, once this transition, it happened when due to some event, maybe this transition has taken place. After that, these are the post conditions where these tokens will be, these post conditions will be generated. Okay. Now again you can see that due to these transitions, you can see these are the edge weights associated with it. That means due to this transition, according to in this place or in this state, one single single transition condition, post transition condition, post condition will be generated. Here for these states, 2 different post conditions can be generated. Okay. So this is your before transition, this is your model. After transition, what is the change in your Petfinet? See, the transition has taken place, and from there, according to this age, you have actually consumed one token. You have actually consumed one transition condition. From this age weight is 3, you have consumed 3 transition. Here it was 3, it is now, there's no token present. Here, according to the age weight 2, you have consumed 2, and after the post condition, now they're coming to the post condition, based on these weights, initially there was already one token present in the state. Now it added 1 due to this transition, and you are having now 2 post conditions. Here again 2 coming based on this age weight 2. So this way now your Petfinet or the places of your Petfinet is not restricted to the number of tokens at each place. Okay. Is there any question till now? Hello?
No.
No? Okay. So similarly, the first one we have talked about the condition or event nets. The second one, the place condition nets. The concept is very similar, only in condition event net, we have just considered one token at a place, and in place transition net, we have just considered multiple tokens based on the maximum capacity of the place. But there's the possibility that these type of nets can also become very large. So that's why to minimize the size, or to restrict the size of Petfinet, there is one modified transition net that is called predicate transition nets, where with each token we are associating some identity, some specific values or some specific types, those things. So in that way we are modifying this net to reduce the overall size. Actually, we will take one example, then I think it will be clear. Then we will see how we can associate the identity with this, net tokens. But what is this type of Petfinet modeling, it is good for modeling this type of immediate dependencies. But the limitation is, when Petfinet was proposed, initially it was not meant for this type of embedded design or complex design. So that time there is no concept of notion of time has been considered. Like if we want to schedule different tasks, that time Petfinet will not be very much suitable. But now there are some time related extensions of Petfinet. So this is the basic limitation and basic usage of Petfinet. Now let's take one example, then I think we will be clear about this concept. Okay. Just a second.
Ma'am.
It's already late, right? Yeah.
We have lab now.
We have lab.
Okay. Then maybe next day we will take one example and we will discuss. Okay. Okay, fine. Okay, one thing I want to. Okay, maybe it's okay. Fine. Tomorrow we will discuss. Fine. That's all for today.
Thank you, ma'am.
Thank you.
Thank you, ma'am.